On November 12, 2025, an automated alarm went off at the LIGO facility in Washington state. Its sensors, designed to detect ripples in the fabric of spacetime, recorded a sharp burst of gravitational energy. This signal, designated S25111-2cm, had traveled 300 million light-years to reach Earth. Collisions between massive objects typically release a blinding flash of light. Within seconds, LIGO software blasted the coordinates to a global network of telescopes, including the Vera C. Rubin Observatory in Chile, to find the expected explosion. Astronomers scoured the region, vetting 456 potential candidates for a kilonova or a gamma-ray burst, but the search returned nothing. Where there should have been a glowing beacon, there was only empty space. This absolute silence is a problem for physics. Detecting a massive gravitational ripple with zero detectable light implies a collision involving objects that are invisible to our current physical models. The mystery centers on how stars die. When a massive star exhausts its nuclear fuel, it can no longer push back against its own gravity. The core collapses inward with extreme speed. Our standard model includes a strict mathematical law for this collapse. It dictates that for a dying star's core to crush itself into a black hole, it must weigh at least 2.2 times the mass of our Sun. If the core is lighter than that limit, a force called quantum degeneracy pressure stops the collapse. The particles literally refuse to be packed any tighter, forcing them to repel each other and leaving behind a neutron star. But the data from S25111-2cm tells a different story. By measuring the chirp mass, the rate at which the signal's frequency increased, LIGO proved the merger involved an object weighing between 10% and 87% of our Sun's mass. This creates a paradox. We just recorded a black hole merger in a mass range where stellar physics says black holes cannot exist. Before rewriting the textbooks, scientists first looked for errors. LIGO's mirrors are sensitive enough to detect motions smaller than a proton, meaning seismic noise or ground vibrations can sometimes mimic a signal. However, the automated pipeline calculated a false alarm rate of just once every 6.2 years. The signal is highly likely to be a real cosmic event, not an instrumental glitch. The next possibility was a stripped neutron star, a stellar corpse that started at a normal mass but had its outer layers siphoned away by a neighboring star. But nuclear physics suggests a subsolar neutron star cannot exist quietly. Without enough gravity to hold it together, the internal nuclear pressure would instantly overpower the star, exploding outward in a massive flash of radiation. Because the telescope hunt from Scene 1 found total darkness, we know there was no explosion. This rules out a neutron star of any size. If the signal wasn't a glitch and didn't produce light, the objects must be black holes, forcing us to look for an origin other than dying stars. To explain these objects, we have to look back to the first microsecond after the Big Bang. In this era, the universe was a hot, dense mixture of subatomic particles colliding at nearly the speed of light. Some physicists, including Stephen Hawking, proposed that black holes could form here without stars. If a pocket of this early cosmic soup was slightly denser than the space around it, the high pressure of the expansion could crush it directly into a primordial black hole. There was a specific window called the QCD phase transition. As quarks bound together to form protons, the outward pressure of the cosmos momentarily dropped. Gravity took over, pinching dense regions of spacetime into tiny black spheres. Because these black holes were born from raw density rather than dying stars, they have no mass limits. They could be the size of an atom or the exact subsolar mass we see in the modern era. S25111-2cm acts as physical evidence that black holes have existed since the first microsecond of cosmic history. This evidence could resolve a major failure in modern astronomy. For 40 years, we've used the term dark matter to explain missing mass. We assumed this mass was made of undiscovered subatomic particles. Scientists have spent billions of dollars building detectors inside mountains and deep underground tunnels to block out cosmic rays. They've waited decades for a single dark matter particle to collide with their sensors. Those experiments have returned nothing. But if S25111-2cm is a primordial black hole, it suggests that dark matter is not a particle at all. Instead of a new subatomic particle, the gravity holding galaxies together may come from an ancient population of subsolar black holes drifting silently through the void since the dawn of time. Confirming this signal means admitting that the hunt for dark matter particles has been focused on the wrong target, and that 85% of all matter in the universe is actually made of ancient black holes.